Good morning and welcome to Tuesday's session. I lost track of the weeks a long time ago, so I think we're at week 13 or 14 or something like that, especially with the spring break that fell in between somewhere. So basically, this is where we are. In terms of content, we have to finish chapter 42, which still have quite a few things to do in it. And then we have to also do chapters 43 and 44. Chapter 43, honestly, is a little bit light in terms of content because it deals with nuclear physics. So nuclear physics is not that intensive, especially in terms of calculations. So that's basically what we have. Chapter 44, though, is going to connect the ideas that are coming from 43, and it's going to delve well inside the nucleons themselves. So it's elementary particle physics, and it goes inside the nucleus, not just inside the nucleus, it's actually inside the nucleons themselves, and distinguishes between the different types of elementary particles. And once we finish with the extremely small, so we started with the hydrogen atom, which is kind of big, and then we get into a little bit of chemistry, the periodic table, and also molecules and things like that and their properties. And we of course, when molecules, this is the chapter 42 that we're still dealing with, so it's still a kind of macroscopic behavior of this structures. Then, as I was saying, chapter 43 deals with nuclear physics, basically how protons and neutrons get together to form the nucleus, and the different forces involved in there, and what keeps the nucleus intact, basically, and stable. And after that, as I was saying, we're going to go inside each and every one of those nuclear element nucleons, basically the protons and neutrons, and find a huge number of other elementary particles other than these two. As a matter of fact, the number is so big that nowadays it's referred to as a zoo, basically, because of a huge number of them. Try to make sense of those, try to organize them. And then after that, we're going to go from that level of smallness, which is extremely small, to the biggest size that you can think of, namely the universe, and try to understand how the universe evolved based on what we know from this stuff, from the stuff that is extremely small. So this is basically how the course is going to end. And in terms of assignments, we still have two major labs. Of course, you're working on a big one too. Actually, the biggest one probably in this class, the one that you have in hand right now, trying to finish it. We still have two more labs that we have to do. We also, in terms of discussions, I think this will be the last assigned discussion, namely the graded assignment. But then after that, I'm hoping that you guys don't lose track of the fact that you follow the discussions, because they will have extreme importance for the last exam. Which brings me to two more topics. I mean, three actually. First of all, the homework, which is a big deal. It's going to have a major impact on your grade, so don't forget that, to finish all of the assignments that are on Pearson. And the second point in here in terms of assignments is actually the post test, which is now actually a required assignment. So we have to spend some time actually discussing the ideas behind it. And of course, we did the pre-test already, so I'm hoping to refer back to the pre-test, not the post-test. The post-test will have similar ideas, so hopefully you guys will have the full understanding of all of the different 8 objectives of this class, so that you have a full understanding of what needed to be covered, and that you should pass that too. And the last one is actually exam 3, which is kind of our final exam, because we don't really have a final comprehensive in this class because of the fact that it is going to cover only the last 4 chapters, namely 41, 2, 3, and 4. Those are the topics that are covered in the last exam, and that is going to be May 19th. So we still have exactly 1 month before this whole thing is over. Okay, in terms of class and everything else. In terms of content, I expect to be done in about 2 to 3 weeks, probably 3 weeks, So the last week will be basically just to make sure that you finish your post-test, and also you do the you prepare for the final exam. Okay, makes sense, everybody?
So could you just repeat where you said that exam 3 is our last exam? So chapters 41 through 44?
That's correct, yes, 41 through 44, and that's going to be May 19th. It's
Okay.
going to be a Thursday, I think. It's going to be during final week. So that's going to be your last exam for this class.
Okay. Sounds good.
Before that, there will be the post test. So it's going to be due on the week before the final exam. And that's actually an important assignment now. It has its own weight. So we still have probably more than half the class is not here. And I was trying to buy some time to see if more and more people will join. Hopefully, at least at the end, other people will join us. And if not, of course, this recording will be made available. You noted that probably some of you that in terms of updating Canvas, it's been a little bit lagging, and I'm sorry for that. But as I was saying, if you really were, if you subscribe to the channel, you would have the content immediately on your lap. But I'm trying to keep up with those things as much as I can. In terms of assignments and in terms of everything else on Canvas, it's up to date. So there is no problem with that. What I was saying lagging was that recording not updated immediately on Canvas when it's available on YouTube. But that's the only thing that is really kind of an issue at this point. Other than that, we are actually up to date right now in terms of that, okay? So the biggest piece of advice at this point in here is to take care of that homework, okay? Make sure, because it's going to have a major impact on the final grade at the end of the day, because once we pull it in and put it in here, it's going to add its own weight to the grade, okay? So right now it's separate. It looks like you have one grade, but then once the other one comes in, hopefully it's very good, then it's going to raise it a level. If it's not that good, it's going to bring it down a little. So you have to be aware of that, okay? So let me first of all find the page that I need to look at, and I'm going to share with you the screen in there, share. So this is the last thing that we did last time, and we introduced the band theory. What I mean by that is that the atoms, as they get together closer and closer to form your material, okay, in general, your solid in this case, each and every one of them, supposedly, when they're far away, when they're in the gas state or even in the liquid state, they're at this point, the energy levels are at the same energy level because they are symmetrical in every single respect. They're actually the same atoms, so they are the same energy level. But as they come closer and closer from one another, the exclusion principle now comes into play. Namely, Pauli exclusion principle would not allow that two fermions, what I mean by fermions is that spin 1/2 basically particles, which electrons are, which means that their wave functions are anti-symmetrical, which means at the end of the day cannot really have two of them in the same state. At the end, then the wave function, the superposition of the two wave function will become null, cancels. So in this case, they shift either slightly up or slightly down to adjust, to give them enough room so that the two electrons basically at that point can be in the same, very close from the same level, but they are different quantum states at this point, okay? So they're fine. So at this point, the energy level far away, when the distance of the atoms basically is big, like in the gas state or in the liquid state, are well defined, okay? So this is, for example, the ground state. This is the state with which all of the electrons are going to be occupied. This is the highest energy level that is going to be occupied. And this is the first excited state, the one that is above it. As you bring them closer and closer, obviously, these two states in here start to split. Each and every one of them splits on its own to accommodate for this compactification, if you wish, of these atoms as they get closer and closer from each other. At this point, there are three possible scenarios. Either there is an overlap, like you can see in here, or there is a small gap, or there is a big gap, okay, an energy level, okay. In the case, for example, of diamond, this gap is 5.47 electron volt. That's a big gap. That's why diamond is actually an insulator. Carbon is an insulator. In the case of iron, for example, or copper, they overlap. So in this case, it's a conductor, because with a slight increase in temperature, even with the smallest one above the 0 Kelvin, at that point, the electrons, the ones that are supposed to be in the valence band, they have room to move, and they move freely, okay? So in this case, that's a conductor. Some materials, though, they have a gap that is within 1 electron volt, slightly less than 1 electron volt, or slightly 0.6 electron volt, or 1.12 electron volt for the case of silicon and carbon. Those are, I mean, when the temperature rises slightly, there is a non-vanishing probability that some of the electrons will find themselves basically in the conduction band. This is called the conduction band now, in this gap structure, okay? And they move, of course, where do they come from? They come from the valence band. So when they move from the valence band, they are available in the conduction band. So they are somewhat conducting of electricity or heat in this case. So they will be available for conduction. And that's not the only process though for conduction. There is another process for conduction for this type of materials. The minute an electron leaves the valence band and ends up in the conduction band, it leaves behind a gap. And we're going to talk about that. You have an empty space, okay? And that empty space can be easily covered by another electron that hops from another atom nearby in the valence band. So as the electron hops to cover that hole, basically we call it a hole because we're missing an electron now that jumped and made itself available in the upper band. Then in that case, it seems as if the hole is moving in the opposite direction than the electron is in the valence band. So I have two processes of doing conduction now in this type of materials. I have the electrons in the conduction band, and I also have the holes in the valence band. So both of them, they will work together to make conductivity happen. Obviously, for a pure semiconductor like silicon and germanium, this is negligible. This is basically of complete insignificance. So it's still behaving for the most part as an insulator for low enough temperatures. As the temperature increases higher and higher, there is more and more chance for the electrons to be available in the conduction band, and more holes open up in the valence band. And at that point, the material becomes more and more conductive. So that's why they are called semiconductors. Semiconductors is because they could potentially conduct under strict conditions. This conductivity, and we're going to talk about that one, enhances drastically in the presence of impurities. And we're going to talk about that. So you can make them really very good conductors, not really to the sense that a good conductor is like copper is, but they can become significantly good conductors with the presence of impurities. And we're going to talk about that, okay? So this is how materials are discussed, classified, and we're going to go in details about that one. So the first items of discussion today is going to be about this distinction between an insulator. This is the last item of discussion, if you wish, in this class. An insulator, a conductor, and a semiconductor from the band perspective, band structure, band energy perspective, okay? However, the picture is not completely clear until we get into the Fermi energy level. So we need to talk about that, okay? So this is the item for the discussion that we need to bring into our attention in here. So let me grab my pen. And so this is the picture then that emerges, okay? In a solid, all of the behavior of in terms of conductivity, for example, conducting electricity, is determined by these electrons that are free to move. Okay, so once they become free, they are really free because at that point they even are not even constrained by the Pauli exclusion principle because they have a lot of room to maneuver. They have plenty of space to go. Okay. So in terms of energy levels, they have a lot of energy levels available for them to be. So there is no chance for them to be competing for similar spaces. So the exclusion principle at that point will not apply. Will basically be completely insignificant for them. So they move freely in this region. The same thing for the electrons that free themselves up and end up in the conduction band. Those two, they end up also in completely free energy levels. So at that point, I can treat them as free gas, basically, of electrons. And that gas is actually has a word for it. They call it the Fermi sea. Okay. So this is the idea. Imagine that I have a bunch of electrons floating in a material, okay, in a solid, and I need to find their density and describe their properties. So the solid has physical size, L and L and L, okay? Before I delve into this picture in here, let me talk a little bit about the crystalline structure because it's important. When the atoms come together, then they can form crystals, and the crystals, they can be as simple as this one, okay? So this is a cubic, or at least called a simple cubic structure, okay? So as you can see in here, I have a cube that is made up of basically 4 balls in this case, and they each and every one of them occupy the ends of it. So in here, so I have a crystalline structure in here, and the crystalline structure in this case will be what is known as this one has an implication later on in semiconductors, and even on so this is called an SC, okay, or simple cubic structure. That's one possible one. Another one where it could end up in the center of it, especially if I have a different materials in here, I could have a center, inside the center of it, I could have actually another atom in there. So that is called actually a body-centered cubic crystal. So basically you will have in the center in here. So let me try to draw this one in here and change just the name, because actually I came up with a beautiful picture. I didn't know that I could do that. I'm sorry. So find the center, which we draw the diagonals, and there is an atom in here. So with this one, it's called actually a BCC, okay? A body centered cubic crystal, okay? Those are not the only ones, though. Those are not the only 3, but I'm talking about the main ones, okay? Another one, what I actually have inside the surfaces, I have another substance, okay? You can't have all 3 of them at once, okay? Another one in here, and another one in here, and another one in here. So there are 6 surfaces, so you should be able to have 6 different individual atoms in here inside of them. There is another one in here, actually. So this one actually is called an FCC, or a face-centered cubic, okay? This structures are important in other properties of the solids. Usually they have to do with the physical properties, like the mechanical properties, like for example the ductile and the physical properties in here, in terms of how much how brittle they are, how much they break, and so on and so forth. So this crystalline structure has so much importance in that, and also it has implications in terms of the conductivity that I'm about to introduce in here. Okay, so as I was saying in here, I'm bringing the atoms closer and closer for one another. I'm trying to put them as close as possible from each other. And this is basically the end structure that I could end up with. I could end up with a crystalline structure, and that's basically the extent with it. Obviously, there is the different types of connections, and the chemical bonding between these different atoms will determine basically the other physical properties. For example, if it's an ionic structure, like for example NaSl, and ACl, which is sodium chloride, then in that case, I will have one electron completely migrate to an atom and from the other one. And that's actually an overlap of two simple cubic structures where each and every one of them will have in the face of it another element and so on and so forth. So this is the arrangement. These are the three main ones. These are not the only ones. There are 14 of them, okay? Different ways of organizing them. One of them is a diamond structure. And actually you have the hexagon in this case that is repeating and overlapping with the others. I tried to make, these are magnets basically. I tried to make it earlier with this ones and I couldn't, so sorry. But anyway, this is the possible arrangements for some of the possible arrangements in a crystalline structure, in a typical of a crystalline structure. So these are crystals in general, or crystallization. Okay, so let me continue with the discussion of the Fermi sea, because that's going to give a very, very important concept that we're going to apply to actually all of these different kinds of materials in here. Okay, so imagine that we have electrons that are free to move in this volume now. So that's basically the picture that we ended up with in here. So we have electrons inside this volume, and there are, for the sake of argument, n electrons. Okay, free electrons for this volume, and the volume is clearly equal to L cubed in this case. Okay, so the density of electrons in this case is going to be n over v. Remember, this is the same discussion that you had way back in chapter 27 when you discussed the drift velocity to find the conductivity of metals. That's the same n, the same charge carriers that you discussed in there. That's the same number of, so this is going to be, the unit for it is basically 1 over cubic meter in SI. Okay, although typically in industry we use 1 over, I mean, in industry they use 1 over a cubic centimeter, because that's more actually a contained number, but don't forget to convert it to a cubic meter if you're given 1 cubic centimeters for the density of the charge carriers. Obviously, this number is very high for conductors. This number is very, very small, or basically not there at all for insulators. And this number is somewhat average between the two for semiconductor. That's really what the whole point of this thing in here. So this number will determine everything at the end of the day. Okay, so let's imagine, since they are free, then in this case, what I have the same problem that we did a long time ago, and that is the problem of a particle inside, a free particle inside a box. So this, I can treat each and every one of them as a free particle inside a box. Okay, and that is from chapter 41, actually. And if we find that expression, because we will need it right away for the free particles inside the box, otherwise we can just basically rewrite it quickly. Where is the? This is the shorting. It's the beginning of the unit. Why am I going to? Yeah, here it is. Actually, I look at it right now. And the energy levels are given by, we need the energy levels. So this is a particle in a box, the discussion we had way back. The solutions are in such a way, none of the quantum numbers can be equal to 0, because if it's equal, if any one of them is equal to 0, the entire wave function will be 0. And we don't want that, okay? Because if the wave function is equal to 0, its interpretation is going to give us 0, basically. And the energy is given by this expression, pi squared h bar squared divided by 2 ml squared, times these quantum numbers in the x direction, in the y direction, in the z direction. They are, each and every one of them are integers, and they are equal to 1, 2, 3 independently, okay, from one another. Okay, so I'm going to copy this expression in here, or rewrite it actually, because we need it right now for unit 42. So the main thing is pi squared h bar squared over 2 ml squared. So the energy then, that depends on 3 quantum numbers, nx, ny, and nz, is equal to pi squared h bar squared over 2 ml squared times these quantum numbers, nx squared plus ny squared plus nz squared. And the wave functions are in such a way that nx and ny and nz are independently from one another the integers 1, 2, and 3, and so on and so forth. None of them can be equal to 0, because if any one of them is equal to 0, the wave function has a sine times nx or sine times ny or a sine times nz in it, and that will vanish from each and every one of them. And if it does vanish, that means I don't have electrons. End of the story. Okay, I have none, and I know I have some, at least for regardless of the material. So the wave numbers in here in such a way that none of them is equal to 0. So this is what I'm going to do now. I have a bunch of them. I have a lot of them. I have n of them, big N of them, okay? And I want to put them in this material. And I want to arrange them in such a way that each time I add more, I'm going to consume some of that energy, okay? So basically, I'm going to pile them up at T equal to 0, at temperature equal to 0, Kelvin. So at that point, I can add them up little by little until I fill up my entire solid of them, okay, all of them. So that's basically the idea behind it. So the first one in here, I can of course put 1, 1, 1. That's the first one. And then I start adding up as I am adding. Don't forget that these are fermions. Electrons are fermions, which means that for each one of these energy levels, I can put 2. Why? Because one of them has a spin up, the other one can have spin down, and I would not have violated the Pauli exclusion principle. They are fine. They were fine with it. So at this point, this is the arrangement that I'm going to do for these electrons. So here is the idea. Instead of working in real space, which has coordinates x, y, and z, I'm going to work in the coordinate of these integers nx and y and z. So I'm going to represent the space in terms of these numbers. This is nx, this is ny, and this is nz. Those are not real coordinates. These are just integers. And they are all positive. None of them can be negative. Okay? So as I'm filling up my states, I want to count how many states are available for me for these electrons, basically. That's the whole point. So the number of states are going to be represented by these numbers nx and y and z that are all in the same octant. Namely, if I take the entire space, the sphere of nx and y and z, then in this case I have a big sphere, but none of them can be negative. In other words, I cannot go into this region of space at all where nx is negative. I cannot go into this region at all where ny is negative. I cannot go into this region where nz is equal to the negative. So the only region that I am focused on for a given combination of these numbers, nx and ny and nz, is this energy state in this case that is given by this expression. So I can think in terms of this space, and I'm looking at this radius in here, where this radius for this state, for this specific state, is given by the square root of nx squared plus ny squared plus nz squared. Okay, obviously, nrs squared is going to be an integer because it's square of a bunch of integers. Okay, so this is a discrete representation. From 1, 1, 1, I have one number. From 1, 2, 1, I have another number. From 2, 1, 1, I have another number, and so on and so forth. So it's not a continuous distribution. It's really a discrete distribution, okay? What I'm looking at in this case is, for this energy level, which I'm going to represent now, instead of representing it as being that way, I just n of radius r for this state. So the s in here stands for the state of this radius, okay? So in this case, it's the surface of this sphere. So basically, it's a sphere whose radius is given by this number, okay? So that is the value of the energy at that point, okay? So this is the energy on that surface. It's given by this expression exactly. And how many energies can I fit in at this point? Every point inside that surface is accounted for before I reach the surface, I have to fill those energy levels first. Because as I start to pile up my big N electrons, I have to start from the lowest. This is at T equal to 0. At T equal to 0 Kelvin, that means that the ground state has to start from the lowest, but I can only put 2 electrons in there. So the third electron has to go to the next energy level, and so on and so forth, until I reach the surface at T equal to 0 Kelvin, where I have filled up all of my electrons at that point. So that is the number of states that is available for my N electrons to fill this material in here. You're asking and wondering about what happened when T is not equal to 0, and we're going to come to it. Okay, we're going to really going into a little bit higher than T equal to 0 and see what's going to happen in that case. Okay, so this discussion is just for 0 Kelvin at this point. Okay, and therefore what I'm interested in is really the volume of the sphere. Volume of the sphere. But it's not the entire volume of the sphere of radius NRS. I'm not interested in the entire sphere. I'm interested only in one section of the entire space, because if I do the volume, which is just 4 pi over 3 times this radius cubed, that gives me the entire sphere, and I don't want that. Those are some of the negative numbers that I don't care for. So I just want the eighth of that, because the entire space is divided into 8 octants of a sphere, okay? 8/8 of a sphere. So I'm just interested in the eighth of that sphere. That's number one. Number two, each and every one of those energy levels can be occupied by 2 electrons, because each electron can have a spin up or spin down. So if they can have a spin up or spin down, I can put 2 electrons in there without violating Fermi exclusion principle. So this is basically the number of electrons at the end of the day, or the number of states in this case that are available for my electrons. So this is the number of states available for this NRS radius. So you're wondering about the energy level on the surface. Well, this is how many available states for it before we reach that energy level. Obviously, there are some cancellations. The 2, the 4, and the 8 cancel. And the actual number of states is going to be equal to, what is it? Pi over 3 times this radius cubed. Okay. There is only one thing that we need to do and get rid of this NRS between these 2 expressions. Because in here, I have the energy, which I'm going to drop in this case, this index of NRS for it, which is just my energy on the surface in here, and given by this radius. So it's going to be relating, so getting rid basically of this n cubed in n squared in here, or n cubed in here. Okay. So remember, let me go back into this expression in here and express the square in terms of the energy level. So NRS squared is going to be the energy times 2 ml squared divided by pi squared h bar squared. I mean, if you're considering, you're wondering what is that, it's just to reroute this expression, that's all. What this thing is actually NRS squared, that's all. The way I defined it in here. Make sense so far, everybody?
Yes.
Okay, so I'm going to take the square root of this expression and cube it to find the number of states. So the number of states then is going to be NS. I mean, the book uses N. I really don't like N in this case because of the fact that we have so many N's in this problem. It starts to become a little bit out of hand. Okay. So it's NS, the number of states, is going to be equal to pi over 3, we need that, times this number, take its square root and cube it. So when it is square root of L, it's going to be, of L squared is going to be L. When I cube it, it's going to be L cubed. And that's actually very good news. We really wanted that. And I will explain why that is later on. But the point in here is, so let me write L cubed because I really need it by itself in here. Then the rest is no problem in here. So when I take 2m to the power basically 3 over 2. So it's going to be 2m to the power 3 over 2 divided by, is it m? Okay, hold on. Is it m? Let me look at this expression here. Yeah, m. Okay, divided by, okay, the same thing what happened in here with pi and h bar squared. When you take the square root, you end up with just pi and h bar. When you cube it, it's going to be pi cubed h bar cubed, okay, times I think there is something wrong in my it's okay, we can figure it out. Okay, it looks like I made a mistake somewhere in there. Okay, and the biggest term in here is of course the energy itself. Did I forget? Yeah, the energy itself in this case. Okay, so the energy is going to be straight out. When you take the square root, is going to be 1/2 times 2, so it's going to be e to the power 3/2. Okay, you can make sure that I didn't get this expression wrong because I may have made a mistake somewhere in there because of that h cubed in the denominator. No, looks like we're good. There is an h cubed in the denominator. Okay, so, oops. The pi cubed and pi cancel. So we'll end up with pi squared in here. And L cubed is just the volume in this case, okay? So, and that's what I was hoping for, is that the number of states will increase with the volume. That means if you double the material, you double the available basically states, that's all. And that's good. It's actually very important to have that, okay? So at the end of the day, this is actually a very important result. What we are actually interested in is dNs over dE. This is what I'm going to define as the density of states. This is actually what we were trying to find, the density of states, meaning how many states are available per unit energy. This is what this expression in here, okay? So the number of states that are available per unit energy, obviously, they're going to drop a factor of 3/2, which cancel this 3. So it's going to have a L cubed, which is the volume, divided by 2. And of course, I have a pi squared in here in the denominator, h bar cubed, times this 2 times m to the power 3/2, and times e to the power 1/2. The square root of the energy, basically. That is really what, oh man, did I lose a page? Yes, so this is the square root of the energy. So if I want to draw this function now, okay, we're still dealing with the energy states. We did not really talk about how many electrons and things like that. So if I draw this, this expression, this is how it looks like. The square root, of course, so I have in here E, the energy, and I here have the density of states, GE, okay? The function is a square root. That means that for E equals to 0, this function is equal to 0. When E grows, this one grows, and it grows for a big value, okay, as a square root in here, as a square root function. So when E goes to infinity, this expression goes to infinity too, okay? But we don't have really an infinite number of electrons. We still have a finite number of electrons, so we're not going to go all the way to infinity. Which brings us to another point in here. And that is, as we're piling up this electrons at T equal to 0, we're going to reach a plateau. We're going to reach a maximum in here because we're going to exhaust all of our electrons. And at that point, that's the maximum energy that we're going to have. So at t equal to 0, we're going to reach a plateau in here. And that is, by definition, the Fermi energy level at 0 Kelvin. Okay? This is the maximum energy that we're going to have because we have exhausted all of our electrons. Here is a problem, though. I took it from E equal to 0, but in my expression, it cannot have E equal to 0. Because this one, and this one, and this one, all three of them cannot be equal to 0, period. They start from 1, 2, 3, and so on and so forth. But this value in here is so small because of an h bar squared. H bar is 10 to the negative 34. When you square it, is 10 to the negative 68. Divided by the length squared, basically the square root, or if you wish, of the volume to the power 2/3. Okay, the volume, so it's going to decrease also with the more material. That's the point I'm trying to say in here. So if you include a macroscopic level, basically on a real material, a real solid that I'm trying to understand, like this object in here, which is really a solid object, has a finite size that is too big. So this expression here is going to be starting, the lowest value is going to be insignificantly small, to the point that I'm going to take it starting from 0. So all of my integrations and summations are going to start from E equal to 0, because it's very, very close from 0. As a matter of fact, it's going to be of the order of 10 to the negative 68 or something like that, or even more, 10 to the negative 70 joules. So this is why I'm practically taking it starting from 0. So that's the first objection. The second one in here is, since I have really a finite number of electrons, I'm not going to have this summation to infinity, because at some point I will run out of electrons. I'll run out of charges, basically. So I'm going to start summing until I reach a point, and that by definition is what is known as the Fermi energy level. Okay, so that is basically the maximum that I'm going to have in terms of energy. In other words, this surface doesn't extend to infinity. Okay, it stops at some point. And what stops it is actually the number of the actual charges that you have in the material itself. Obviously, for a conductor, you still can go very far, but for an insulator or semiconductor, this sum can be a little bit finite. So let's see in here how this distribution is going to be. Okay, and I'm going to introduce a function in here without having to put the proof for it, because the proof is actually outside a little bit of the scope of this class. It uses statistical physics that we use in chapter 18, actually. Okay, start from that point with the following two requirements that are extremely important. When we did statistical mechanics, Boltzmann's Maxwell statistical mechanics, we were dealing with macroscopic atoms, basically, or macroscopic molecules, hydrogen and, not hydrogen, nitrogen and oxygen and all of that gas. And we made the assumption that maybe somehow they are distinguishable. Okay, you can differentiate between them. So the first requirement in here is that these electrons are actually indistinguishable. In other words, you cannot tell the difference between this electron and this electron. They are the same particle for all practical purposes. That's one property. The other requirement is two of them cannot occupy the same quantum energy levels. Namely, for the same NX, the same NY, the same NZ, and the same spin, you cannot. You have to have at the end the exclusion principle that requires that no two of them can be in the same state. If we put this requirement and go back into the expression that we did for basically when we introduced omega, which is the macro state in that case, trying to define the macro state in terms of the distribution of the microstates, we'll find a new distribution function that is not given by Maxwell-Boltzmann distribution, but rather given by this function that I'm going to give you right now the expression for it. The function is 1 over exponential of what is the what do I get back into this page? I hate this page. The energy, which I'm trying to draw the function for, minus EF divided by, I'm going to explain each and every one of these terms in here, plus 1. Okay? So this is called the Fermi Dirac, no, not Dirac, C, Dirac distribution function. As opposed to Maxwell-Boltzmann distribution function, because these particles are bosons because of this requirement. I'm sorry, not bosons, fermions. If they were bosons, this expression will have a minus in it. Okay, that's Bose-Einstein particles. Okay, Bose-Einstein statistics. Now, this EF, first of all, has to do with something called the chemical potential. As you add particles individually or remove particles individually, that is actually what the chemical potential is. That is actually how much energy is needed to add or subtract. And this is what we're doing. We're adding until we reach that point. So this one is related to the chemical potential. For case of the metal, it's called the Fermi energy level. And the reason why I don't have 0 in here is because this is not at T equal to 0, but this is at any temperature T. And this is the distribution of the energy of these particles as a function of their energies, basically. Okay, so this is how this function looks like. So if I want to graph this function, obviously at T equal to 0, this expression in here will have two values. Either E is more than EF or E less than EF, one of the two. Okay, so this is at T equal to 0, the way I'm going to plot it right now. If this term is 0, that means this expression blows up. 1 over 0 is infinity. But the question is it positive infinity or negative infinity? That's all. Okay. So if E is more than EF, this is positive. And positive over 0, that is positive infinity. An exponential of positive infinity is infinity. So this term will go to infinity. And if it goes to infinity, 1 over infinity is 0. So at this point, the function, so I'm going to draw the function itself. So this is F. The distribution function is a function of energy. So we have the cutoff frequency in here, which is EF. Cutoff energy, in this case, it's EF. As a matter of fact, at T equal to 0, we're talking about EF naught. Okay? We're talking about the same energy, Fermi energy level at T equal to 0. So when, let me change the pen quickly, and probably even the thickness of this, because I want to see the, so this is what I'm talking about. This is when E is more than EF for the case of T equal to 0. For the case that T is actually, for the case that E is less than EF, at the same time, we're still dealing with the EF naught, that means this number is negative. An exponential of negative infinity is actually 0. And 1 plus 0 is 1. 1 over 1 is 1. So this function is 100%. So it's 1 when EF is less than, when E is less than EF. And obviously there is a transition point in here. Make sense, this graph, or not?
Yeah.
Okay, so the question then, is everybody on board too, or is just one of you guys are awake today? Does this make sense to you guys?
Yep.
Yes.
Okay, very good, very good. So here is the point then, that at T equal to 0, all the energy levels below the Fermi level are filled. Not a single one of them above the Fermi level is filled. So that's exactly the picture that we were talking about earlier, that by definition, in this case, the Fermi level is the cutoff where all of the energies are filled up to that point, okay, at T equal to 0. Now what happens when T is not equal to 0? And if I want to draw this function, well, this function behaves as follows. Depends on T, of course. Let me go back into my drawing pen. Probably I should draw it in a different color. So this is slightly above t equal to 0, if you wish. There will be deviation. First of all, if I evaluate this expression at E equal to EF, at E equal to EF, the exponential is just 0. And the exponential of 0 over, we're talking t is not equal to 0, slightly above 0, even if you wish a fraction above 0 Kelvin. So it's going to be 0 over something. It's going to be 0. Exponential of 0 is 1. 1 plus 1 is 1. So it's going to be 50%. So this is basically the cutoff. So this is 50% or 0.5. Okay. But all of them, they will pass by that point. All of the curves that I'm going to draw right now at different temperatures, they will pass by that point. Because no matter what the temperature is, when you put E equal to EF, 0 divided by any number is going to be a 0. Exponential of 0 is 1. 1 plus 1 is 2. 1 over 2 is half. So this graph would look like this. It's going to go to 0 at infinity, because when the energy goes to infinity, no matter what the temperature is, it's going to be e to the power infinity plus 1, which is infinity. 1 over infinity is 0. When e goes to 0, this expression will go to 1 again for when this expression, because this term will become so small at the end that you're going to be adding 1 to a small number. 1 over 1 is going to be practically 0, but it's going to be below. Okay, but here is the thing, though. At a different temperature, higher than t equal to 0, some of the electrons are below the energy level. Not some, the vast majority of them are below E equal to 0, but some of them find themselves above. I mean, not above, above the Fermi level. Those are the ones that are conducting. Because if it's frozen, there is no conductivity. If it starts to get heat a little bit in normal temperature, room temperature, then you have plenty of charges that can move. And that's the point in here that I'm trying to make in here. So this is basically how we can interpret this one. So if I go back to my, first of all, I need to find this energy level at t equal to 0, at Kelvin t equal to 0. And for any point in here in space, we really have to take, first of all, the density of energy of energy in this case, this density of states in here per unit energy. Basically, this is how much we have, times, if I want to fill up my electrons, times this function itself that tells me how many electrons can occupy a given state. Okay, times the energy, in this case gap. So this is the probability, if you wish, of finding electrons at a given energy state. Okay, so this is dp, and it's a number at this point, because this is 1 over energy, this is energy, energy cancels, this is unitless anyway, so this is actually a number, the probability of finding a certain electron at a certain point in here at a given temperature. Okay, so if I want to find, for example, my energy levels, my Fermi energy level, all I have to do is go back into this expression here and require that it's equal to, what is it? This expression here, and require that this number, actually, what is it? This one in here is the number of states are all occupied by the number of electrons. So if I have n electrons, remember, I already accounted for the Fermi, for the exclusion principle in this expression already for that volume when I multiplied by 2 in here. Okay, so in this case, in this case, the number of states represent actually the number of electrons. So in this case, it's going to be equal to this expression, which I'm going to write it as volume times, again, 2m to the power 3 halves, 2m to the power 3 halves, divided by, I have a pi squared in the denominator, and I have a 3 also. 3 pi squared times h bar cubed times the energy level now, the Fermi energy level to the power 3 halves. Okay, so this is the expression that I end up with for the Fermi energy level at 0 Kelvin. Okay, honestly, if I want to find it for any other temperature, I really have to carry this calculation, and this is not a simple calculation. I really have to sum for all of my electrons up to that point in here, and this summation is not an easy one because you have an e to the power 1/2 coming from GE, and you have this complicated function of e, and that involves special functions, okay? That's not going to be something easy to carry out. Other than that, this is how we find the Fermi energy level at 0 Kelvin. As a matter of fact, we can find it as EF naught is equal to, all I have to do is just rearrange these things in here. Remember, I have N over V in here, and I need N over V in here to the power 2/3, because I have everything to the power 3/2 in here. And if I do to the power 2/3 in here, it's going to be 2m period, okay? And if I take h bar to the power 2/3, it's going to be h bar cubed, h bar squared, because 2/3, the third cancel the third, and the 2 becomes just squared in here. And pi squared and 3, I'm going to leave them as is, 3 pi squared to the power 2/3, okay? Other than that, this is the expression for the Fermi energy level. That we need to be concerning ourselves with. Okay, the reason why I'm saying that is because technically this term depends on the temperature. This function depends on the temperature. That's why I'm addressing it with 0. Even in the pre-test, the question that was given to you had to do with this term. Okay, you cannot calculate it. You don't have an expression for it. So typically, what we have N over V. N over V is the density of charge carriers. So how many you have of them? Okay, for the material. So if you know that, then you know what the energy Fermi levels is, because especially for electrons, we know what the mass of the electron is. For conductors, that is, for normal conductors, for metals, we know what M is. M is just the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms. Okay, when it comes to semiconductors and other materials, it becomes a little bit more complicated because the mass actually is an effective mass, not a real mass, okay? So it becomes a little bit slightly off, but it's not going to be too far from the mass of the electrons because it's still really they are the ones who are doing the conduction, okay? But you can find what the expression for M is. For this case in here, for all practical purposes, we're going to use the mass of the electron in this case. Each bar is just a constant. Each bar, by the way, is what? 1.055 times 10 to the negative 34 joule second. Remember, it's just H divided by 2 pi. Okay, what H is at 6.626 times the same power. Okay, so this is what we need to do. So let's put some numbers in here. Let's put some numbers in here for a conductor in here. Okay, and I think there is an example in here for your. For copper, I think was the pretest, some material, I think it's iron or some other metal. For copper, we have N is equal to 8.45 times 10 to the power 28 per cubic meter. So we can find what this energy is. Okay, the number should be anywhere between 1.5 to about 16 or 17 electron volts, okay, for conductors. So if we do the calculation in here for the Fermi energy level for copper, we need to plug in the numbers in here. All we have to do is 3 pi squared. 3 pi squared is like 12, okay? It's just a constant. Okay, so just a number. Okay, so don't I mean, obviously, for a question like the pretest, they give you so many close numbers that you probably have to compute it, okay? 2 times that number, 2 times the mass, 9.11 times 10 to the negative 31. Here is another point in here. This Fermi energy level depends on the charge carrier's mass, okay? Which is kind of interesting in here. The smaller it is, the higher this value is, okay? And then times this density, and that's really the point in here, times this 8.45. That's what makes the difference between, oh, I forgot H bar. is 10.55 times 10 to the negative, what is it, 34? The whole thing squared, okay? Don't forget each bar squared. It's going to throw you off big time if you forget it. Times this number to the power 2/3, 28 to the power 2/3. Before I do that, from the get-go, I'm going to divide by 1.602 times 10 to the negative 19, because I want this expression in EV. I don't want it to be in joules, okay? So if I do that, let me stop sharing. And let me share with you Mathematica. And let's plug in the numbers, okay? As they are. I'm not going to even start messing around with that. So the first thing in here, I have 3 times pi to the power, parentheses 2/3, times h bar 1.055 times 10 to the power, open parentheses. I'm not sure exactly how that's going to handle the, I don't want to take chances with this thing, squared, times, squared first, times the density 8.45 times 10 to the power, open parentheses 28, and the whole thing is to the power 2/3, to the power 2/3, divided by the denominator has a 2 in it, has the mass of the electron, 10 to the negative 31. Okay, probably I should put it in parentheses in here. Okay. Times the charge of the electron, which is 1.602. Just that is to convert stuff to electron volts. That's all. Because usually, typically, these things are expressed in electron volt, 10 to the power negative 19. Because 1 joule, I mean, 1 electron volt is 10 to, with 1.069 times 10 to the power. Did I close this parenthesis? Yes. Okay. So it's giving me 3.27 electron volts. And why am I off in here?
I think the beginning should be 3 pi square, right?
Oh, good, good. Thank you for picking up on that one. Pi squared, okay. Okay, 7.03 electron volt. And we are within that range. Okay, we are within that range. So it's good that you guys need to be, when you see mistakes like this one, that means you have to be focused when you're doing these calculations in here. So we go back to the notes. So this is the main thing in here. This is the Fermi energy level. This is a very, very important concept that we arrived at. Okay, so this is basically the picture that we are. Before I do that, let me find the total energy in this case. For the entire gas, okay. If we find the total for the entire gas, for the entire solid in this case, okay, of this electron. So the total energy, again, it's given by that probability just times E integration from 0. And again, warning about the 0, it's coming from the fact that it's practically 0, all the way to the energy that we're considering in here. But I'm going to go to a special case in here. I'm going to go to the case where t equal to 0, because as I was saying, this calculation is very hard to do in general, okay? So it's going to be from 0 to EF of t, which is very hard to do, as I was saying, of E times G sub E times, because this is a probability, so you have to still multiply it by E in this case to find energy. Otherwise, you're going to find a dimensionless number. You're going to find 100%. If you sum up really everything in here. E, D sub E, okay? This E cancels the 1 over E in here. This one is dimensionless, and this is a total energy, so it's going to be in units of electron volts if we convert everything to electron volts. As I was saying, this integral is not easy to carry, okay? So what we need to really do is go back to the approximation that we're back into around t equal to 0. And so this integration is going to be from E to EF naught. And this expression will just become 1 from 0 to EF naught and 0 anywhere else. So the integration is going to be E, actually, why not F naught? It's the entire energy, so in this case, all of it, okay? So in this case, it's going to cut off still at EF naught if we do this. So it's going to be the total energy in this case is going to be equal to the integral from 0 to EF naught of simply E, G sub E times 1 times DE. Anything else for FE is approximated to 0. Okay. As a matter of fact, even if we did the drawing of the graph, even for higher and higher temperatures, F of E really doesn't diverge very much from 1 for the most states and below the energy level. Okay, below the Fermi energy level, and it doesn't go that much above the Fermi energy level, but just enough for the conductivity to happen. Plenty of it. So we do this calculation. It's just basically rearranging this expression in here that we have found for EF naught in GE. This is the expression for GE. This is the expression for EF naught. And just basically reworking this expression together and finding the value in here. It's not hard to do this integration because at the end you will have an E times square root of E integrated. So it's going to be E to the power 3/2 dE. So the integration at the end of the day is going to be 5 over 2. I mean, the power of 5 over 2. And this flips to 2 over 5. And you just carry the calculation all the way throughout. Do you guys see that this is doable calculation? GE is given by that big expression. Let me rewrite it in here. It's a mouthful, really. It's V times 2m to the power 3/2 divided by 2 pi squared h bar cubed. Man. Can I copy this? Is there a copy and paste in here? Control C. Oh, yeah. Okay. So I forgot the H bar in here in my copy in here. So I need to include that now. This is supposed to be H bar, okay, cubed. That's it. And there is the other leg of pi. Okay. So the copying, those two were done. Anyway, this is the expression. We multiply by E, you integrate it, and you try to express at least V in terms of EF naught. If you do that, you will find that the energy, the average energy at T equal to 0 is going to be about 3/5 of the total energy, the average energy, which is really E total divided by N, is going to be 3/5 of the Fermi energy level. You guys see that this calculation is doable? Yes. Because at the end of the day, all I'm integrating is from 0 to EF naught. So I'm going to have an EF naught at the end of the day of E to the power 3/2 dE. Makes sense or not?
Yeah, that makes
Can you
sense.
guys? Yeah, okay, very good. You can go from here to here. Don't forget that the average energy in this case is just the total energy divided by N. Because if you don't do that, you'll end up with an N in here for the total. Obviously, the total energy will depend on the number of electrons. The more electrons you have, the higher the total energy is going to be. So that's why we're defining E average, and E average will depend on just that EF naught. Okay, so it's going to be, in other words, if I go back into my distribution here, so this is where the E average in here, somewhere in here. Okay, so this is what the average energy is going to be. Okay, so that is basically what the point in here of this whole argument is: 3/5 of the total energy. Okay, so we have an understanding. This is basically what happened with conductors. So we have a full understanding of it. So you have electrons that are available for conduction and above the Fermi level. There is no problem with it. What happened when you have gaps for the case of semiconductor? So this is the valence band. This is the conduction band. And the gap between them is represented by the gap energy, which is equal to basically the difference in the energy between the valence, the conduction and the valence. Okay, so that is what Eg is. Okay, that's what this is the gap energy. Remember, there are energy states below EV that are filled to the capacity with electrons. In the case of heated up materials, like for example, the case of semiconductors, and even for an insulator, if you wish, could have few electrons, but not enough to really have a significant conduction, that end up in here. Okay, it's partly spaced in here. Okay, the Fermi energy level in this case is going to be smack in the middle. So this is the energy level. Usually for the material in this case is going to be, if the gap is big enough, too big, like for the case of diamond, as I was saying, Eg is 5.47 electron volt, okay? And if I want to heat up the material, let's say, for example, what happened at room temperature. Do my electrons have enough energy to overcome this gap? Let's check, okay? On average, if they're really freed by the equipartition theorem, they will have a kinetic energy given by, on average, of 3/2 of kBt. Okay, while kb in this case is 1.38. This is from chapter 18 and before, times 10 to the negative 23 joules per Kelvin. Okay. Again, we really need to work in the units of EV, okay? So I'm going to divide this one by 1.602 times 10 to the negative 19 joules for each electron volt. Cancel this with that, and then the expression now makes sense to write it in terms of in electron volts per Kelvin. Okay, because we have everything in LAV, so it's better to have it. So let me divide that number quickly, 1.38 times 10 to the negative 23. 10 to the negative 23 divided by 10 to the negative, that's 10 to the negative 19, 10 to the negative 4, I mean in here. So this one cancels that, and I will end up with 10 to the negative 4. However, 1.38 divided by 1.602, that is going to actually be 0 point something. So I really need to divide 13.8 divided by 1.602 and make this one 10 to the negative 5. Okay, so it's going to be a very tiny number if I do 13.8 divided by 1.602. That's it. That's all I need to do now, because it took care. So this is 8.6 times 10 to the negative 5 electron volt, 86 micro electron volt. So it's not anywhere really of energy per Kelvin. So even at room temperature, when T is about 300 Kelvin, the energy that we're talking about, 3/2 times this number. So the energy that we have for this electron is going to be 3/2 times this number, 8.6 times 10 to the negative 5 times 300. So even that number is going to be not enough to cause much of a headache. So it's going to be 3.5, which is 3 over 2, which is 1.5, times 300. Okay. So times 3, because I know 300 is going to bring up 2 of those powers and make it 10 to the negative 3. And then the value in this case is 3.87 times 10 to the negative 2 electron volts. So it's 0.0387 electron volts. So it's not going to cause much of an electron to jump from the valence band in the case of an insulator all the way to the conduction band. Do you guys see my argument in here? This gap is too big for thermal excitations to really cause much of a jump. Make sense?
Yeah.
Okay, very good. Even with other mechanisms of excitations, let's say, for example, we shine a very intense light on it, it's not really going to give me much of an energy to overcome this gap for the case of an insulator. Okay. As a matter of fact, this is what we're going to do. We're going to consider this gap to be 0.2, which is very small, 1, which is small enough, but it's 5 times as much as the first one, and 5 electron volts, and see what's going on in this case. Okay, if we calculate the values of Fe, okay, which is really the probability that we're going to have in here. The energy Fermi level in this case is going to be smack in the middle. So the difference between this and the Fermi energy level is going to be just 1 over exponential of half of this number. So it's going to be, this whole gap is, I'm saying it's 0.2. But divide that by 2, it's going to be 0.1 divided by kBT. Remember, kBT is just this number that I just wrote, kB times the temperature. And I'm going to take it at different temperature between 300, just like, and 310, and see exactly what's going on in here. So if we do that, this number is just 8.6 times 10 to the negative 5 times 300 plus 1, okay? So for the first case, and if I do the calculation, so basically how much I have a possibility for an electron that jumps into the Fermi energy level, and from there to the whole gap, if you want to do that. So in this case, you will find that these numbers are very, very, very small in here, okay? Regardless of which level we are, but it's going to be more significant for this one than this one. It's going to be actually about 1% or 2% for this one. And in here, it's going to be a ridiculous number, smaller and even smaller. So the point being in here, even for a semiconductor like this one, it's still, the gap is too big for thermal agitations or even normal processes to excite those electrons and bring them from the valence band to the conduction band. Okay, so this is the point in here that I'm trying to argue in here, that the gap is too big usually, especially for an insulator like the diamond I was talking about. For silicon and germanium, this number is usually a small number. But here is how the conduction happened for semiconductors, which brings us to the, okay, we still have about 5 minutes, I guess, from the time. But let me tell you exactly what we need to do right now. And it's not much left in this chapter, by the way, okay? We're going to consider a semiconductor. So I'm going to exaggerate the gap a little, okay? So this is still the valence band. This is still the conduction band. And this is still the Fermi level in this case. It's going to be called the intrinsic Fermi level because this is how normal, basically, semiconductor is. Okay, this is either silicon or germanium. Those are the two types of that exist in the periodic table on the 4th column, just below carbon. Okay, you look at the carbon in the periodic table, you have carbon, then you have silicon and germanium, and those are on the 4th group in the periodic table. In other words, they have 4 electrons at the outer shell to participate in bonding, just like carbon is, with the exception that carbon, diamond, I mean, the diamond that I was talking about in that case is an insulator, okay? But this one, they have actually a small gap where this thing can become significant. So again, we're going to talk about electrons making it in here, not too many of them, okay? So those are responsible for conductivity with the temperature, with the increase in temperature as I was describing before. And as they migrate, they leave behind holes, okay? What appears to be positively charged particles with similar mass and also same charge moving in the opposite direction. So if I apply an electric field, let's say, for example, in this direction, well, the electrons have a negative charge, so they start moving this way. The electrons that are in here, bound to their silicon atoms, they actually find an empty space in here and they jump in it to fill it. And the same thing with the electron in here. As it moves, it leaves an empty space. So another one will fill it and another one will fill it. So the electrons in here are happening as if these holes are actually moving in the same direction with the electric field. And both of them, because the current is in the opposite direction of the motion of the electron, so this will result in a current in this direction, and this will also result in the current in the same direction, but this current is due to the negative charge, and this one is due to the positive charges. The combination of two of them is actually what makes the conduction in a semiconductor. Okay, so we're going to explore this idea, but as I was saying before, this idea is really not that great, okay, by itself for a semiconductor, silicon and germanium by itself. So in the presence of impurities, this is what's going to happen. There are two types of impurities. The impurities that come from group 5 in the periodic table, namely arsenic, for example. So in this case, the Fermi energy level jumps and becomes so high in this case, okay? So this is the Fermi energy level as it is adjusted by the impurities, the presence of the impurities. In other words, the electrons from the impurities will hop and find themselves in the conduction band. And this type of conduction obviously is of the type N. So this is an N-type doping. If I add elements from the 5th group in the periodic table to my silicon, so I move the Fermi energy level higher, close from the conduction band, so that the electrons, they can make that jump of usually 0.01 electron volt easily, because 0.01 volt electron volt is less than 0.03887 for the vast majority of the dopant electrons, basically free electrons, they find themselves in the conduction band and move. That's it. So this is an N-type doping. In the case of a P-type doping, basically take an element from the 3rd group in the periodic table and put it on the semiconductor, the Fermi energy level drops closer to the valence band. So in this case, the gap will still be 0.01 electron volt, about that number, and this gap is very small compared to this one. So all of its available energy levels will be occupied by these electrons that make up this hop in here. So all of this available energy levels will be filled. Obviously, they're not going to be conducting anything, but they leave behind holes in here as they move, and these holes now are positively charged, and they are going to be responsible for the conduction. So in a P-type doping, so this is a P-type doping, basically taking elements from the 3rd group in the periodic table and put them together with the silicon and basically cook it, warm it until they distribute randomly. And now those impurities will make energy levels available for them to be occupied, basically grab the electrons of the silicon, take it from them, or germanium, and then at that point there is a hole left, and that hole now is responsible for a connection. So this is a positive type doping in a sense that you'll have a P. The combination of an N and P are what makes semiconductors useful. It's the doping that makes it useful, not the intrinsic behavior, not this one. This one is really, if you take because silicon is nothing but the rock that you find on the sand. If you go to the sand on the beach, for example, or somewhere else, or the playground, that is actually what silicon is. It's useless, okay? But when you dope it properly, either within N-type materials, these are called acceptors, donors, and these are called acceptors. So in this case, you will result in a significant conduction. Of course, it's going to be in one direction or the other when you join the two. Makes sense so far?
Yes.
Okay, very good. So we're going to delve into this idea a little bit more on Thursday when we meet. The lab this week is really a breeze. It's not hard, okay? So we're going to finish this one, maybe introduce 43, and actually go into the lab and see how we're going to do the applications. We'll probably leave the application until we're done with chapter 44, with all of these chapters. Sounds good, everybody?
Sounds good.
Yeah.
Okay, so I'm going to stop the recording and I will see you guys on Thursday.